All right, so these are going to be the graphs from lesson set 43. Let me get a full screen so I get a better chance of focusing the camera on the calculations we're going to look at. So I've got what, 106 over there, 88, 12, 18 graphs. Each of these graphs should take 10 seconds, and that's the goal. That's not going to be the case when you're first learning them. But as I look at something like this, I would anticipate that I could sketch it in 10 seconds or less. But then I gotta get a lot of experience with it. The only way you're gonna get experience with it is to practice. So that's what we're gonna do now. I'll write the first function 4 different ways and see if you're starting to grasp what's going on. All right, so the first way I'll do is a sine function. 50 to 100 means that I'm centering at 75 and I've got a 25 amplitude up and down. I'm going to do it as a sine function. Right now, this is addition, so I've got to make this a minimum, and the minimum occurs at 3 pi over 2. That's where we get the sine of 3 pi over 2 gets us -1. So I'll build this off of that linear calculation here. I want to make a 0 out of 210, so x minus 210. Didn't leave myself enough space here, so well, I can ram it in. Okay, and I'm going to stay at 3 pi over 2. So now if we put in 210, we get a 0. It doesn't matter what the multiplier is. The sine of 3 pi over 2 is -1 times 25 minus 25 plus 75. That nails that. And we've got 1 revolution is 2 pi, 4 pi, 5 pi, 2.5 revolutions, which takes 210 to 240, 30 years. I don't care if you reduce that. I'm looking at the process here. Now here's the 4 ways to do it. I could have made this a minus, right? And a minus means that I want to have the max. So instead of 3 pi over 2, I write pi over 2. Same function. Could have done it as a cosine. You need to know that the cosine of 0 is 1 and the cosine of pi is -1. So which one do I want? I want to have a negative, so I'm going to make this thing be just 0. All right, and so now when I drop 210 in, I'm at 0. I'm at that location of the circumference of the circle, which is a +1 times -25 gives me that. And if I wanted to measure from pi, all right, pi gets me -1, so I'll add, right, because this is going to become -1, gets me that. So that was 4 different ways of doing that. Yes, probably more ways than that, but they get a little more challenging when you're not working with 0. All righty, 819, x minus 8 squared plus 19. Can I just maybe say all of these are y equals, and then I don't have to write y equals anymore? I don't. 19 to -5, it looks like I'm going down 24 units. And when I drop in 15, 15 minus 8 squared, I'm going to say it that way from now on. 15 minus 8 squared is 49, and 49 units plus 19 doesn't take me there, but that number plus that number does. Exponential model. So we've got to look at the differentials. 10 to 50 is a jump of 40. 10 to 90 is a jump of 80. Looks like we got a 2 to 1 ratio. So therefore, I'm going to measure from 10. My first jump is 40. My next jump is twice that, 40 to 80, twice that, but I'm going to write it as 80 over 40. If this had been 81, I would have put a 1 there and I'd be a little more than doubling and I would have gone up to 91. 1903, so x minus 1903. 1903 to 2000, 97 years. Drop it in 1903, you get a 0. 2 to the 0 is 1, times 40 is 40, plus 10 is 50. Drop into 2000, you get the exponent 1, which gives you 2 times 40, 80, plus 10, 90. All right, the inverse of exponentials, logs. So I'm going to start with y here, because that's definitely 50. And I know how I get to 72. I add 22, I know it's a logarithm. Asymptote at 4, so I write x minus 4. I look at my first differential, which is 3 units. So now when I put 7 minus 4 over 3, I get log 1. I know what log 1 is. Regardless of any base, I know log 1 is 0. 0 times anything is 0 plus 50 gets me 50, gets me my domain restriction. I drop a 10 in. 10 minus 4 is 6 divided by 3 is a base 2. I'll write it this way, but hopefully you can see this is 4. How do I get to 10? There's my 6. Okay, so that means my next one's going to be 12. Next one's going to be 24, so on and so forth. And then this one's going to be 3 halves, 3/4, so on and so forth. All right. Just a linear function. I hope you're putting, I am flying here. I hope you're pausing the video before you pause the video. You try them all. I'm just giving you the answers. All right, so I see 5, -4. I see I'm going over 1, up 2, over 1, up 2. There's my point slope form. Might as well nail this one. Over 1 makes it 6. Up 2 makes it -2. So it passes through those 2 points and it's linear. Pause the video. Sketch. I'm seeing that. I'm seeing this. I'm looking at, well, I'm looking at minus 3x minus 24. I want to know when that's 0. And, well, all right, that's a new way that I'm doing this. Let's go back to the old way. Minus b, 24 over -6 is -4. See, that equals -8. So what I really know is one of my roots is always 0, right? Because this is x times minus 3x minus 24. So if you set that to 0, you always get one of your roots centered at what's not necessarily a root. 0, 2 would be part of your graph. So would, in this direction, -8, right? So the vertex is always halfway between those roots. So I'm looking at that saying -8 cut in half -4. That's how I'm doing it now. But minus b over 2a is 24 divided by -6. That's just as fast. But I think this leads you towards something that's interesting. So I plug in -4, I'll cut it in half, -2, -48 plus 2, -46. I just made a mistake. -4 times -24, I want to cut that in half. Minus 24 times -4, I want to cut it in half. So I'm going to divide it by 2. So I think it's easier to do that right now. So -2 times -24 is positive 48. Positive 48 plus 2 gets me 50. Okay, and I know 0 is over here. 0 gets me positive 2. And I actually know I'm going down at 24 to 1 right there. And that's been discussed in a lot of the earlier lesson sets. All right, e to the x and e to the x. Your teachers are probably talking about transformations. I work with e to the 0 and I work with e to the 1.1. I standardize this to always be a 3 to 1 ratio. So discussing that, go to the playlist, look at the standardization of the graphing, 5 practice problems, and you'll see the following. All right, so y equals -4, that's our asymptote. I'm going to go up 10. I'm going to make this go up 10, then I'm going to make it go up 30 by picking the correct exponents. This, I want to be that. So I can see that that happens at 1. 10 minus 4 is 6. So this goes through 1, 6. And then I want 2x minus 2 to equal 1.1. So that's 3.1 divided by 2. 3.1 divided by 2 is what? 1.55. So 1.55 should get me e to the 1.1, which is 3, which is a jump of 30 minus 4, which is 26. That's not, this is an approximation, right? But it's a darn good approximation. So then you erase your differentials. And you get some practice with that in the playlist. Same thing, playlist. There's 5 of these. So I'm looking at what makes this 0. I'm looking at what makes this 1. And I'm looking at what makes that equal 3. Because those are going to be friendly numbers. So what makes it 0? -1. That's my asymptote. All right, so that gets you the asymptote. ASYMP. All right, what makes it 1? Subtract 2, -1, divided by 2, -1/2. That gives me 1. What is the ln of 1? Log 1 is always 0, so I get rid of that. I end up with the constant. This is a negative ln, so actually it's going to be coming this way. So I really should have repositioned that. Well, that's okay. We can get it done. 2x plus 2 equals 3. Maybe that's the one I just did here. Okay, so that's equal to positive 1/2. Okay, just caught me off guard for a minute. So if I put 1/2 in here, I get 3. The ln of 3 is 1.1 times negative 2 is negative 2.2 plus 2 is negative 0.2. Negative 0.2, and that's a half. So I got to put it here, which I kind of realized, you know, it's going to look like that. Now remember, this eventually decreases very, very slowly, very, very slowly. This is the inverse of decay. All right, and it could have done a better job, but we're most of the way through the video, so we're just going to keep on rolling, right, Renee? Yeah, keep on rolling. All right, so I'm going to look at this from the standpoint of more of a textbook standpoint. So I've got a positive cosine, so I'm going to go from max to max. The period is already given here. 1 revolution every 9 units. So I'm starting at 1700. And 9 units later, 1709, I'm back to a max. And my max is going to be 5 plus 10, 15. And my midline is 10. And therefore, my range is from 5 to 15. And I've got 1 period. And that's all I've been asked to display is 1 period. All right, so let's move on. Come on, Renee. Make a turn here. Yeah, need my coffee. I need my coffee. I'm having trouble driving. All right, where are we? Can we see this? Yeah, all right. So I can see there's no x-intercepts. There's no way to make that fraction equal 0. I can see that I have asymptotes at x equal plus and minus 5 if I put it in factored form, which I'll do for you now, x plus 5, x minus 5. All right, so I might as well start sketching 5 and negative 5. I know it goes to 0. Keep putting bigger and bigger numbers in. It's easier to see that back x squared minus 25. Just start putting numbers in, make them bigger and bigger and bigger and bigger and bigger. 10 squared minus 25, 1,000 squared minus 25, 1,000,000 squared minus 25. Doesn't fit into 3 very much at all. So I know it looks like that on this side. I'm going to get sign changes. So let's go back to x plus 5, x minus 5. Okay, so right here, it's the first degree. That means I'm going to go from positive to negative. Put a number bigger than 5. You get a positive parentheses, put a number like 4 in here, you get a negative. I get a sign change with a multiplication. 4 and 6 do not affect this parentheses. It's positive when it's 4 or 6, but they get a sign change here. So I got a y-intercept back to x squared minus 25. If you put 0 in, you should be able to tell me that you're right about there. Negative 3/25. I'll put it on this side. There are no x-intercepts. So this has to do this. It's got to do that. I almost wanted to go cut through the x-axis, but there are no x-intercepts. So it probably got some symmetry here. But then I get another sign change if I put it back into factored form. I get a sign change near negative 5. Put in negative 4, put in negative 6. You'll see what happens. So it should look like that. Y equals 0 over here. All right, so what is the limit of this function as x goes to infinity? The bigger the number in, the closer you get to 0. What's the limit as I approach 5 from the right? Well, from a numerical standpoint, 5 from the right means I'm tucking the number 5.01 right in that location, right there. And that's going to get me a very small 0.01. And if I multiply that by something near 10, Well, that's just making the decimal place move one spot. But I can create a very, very small number, and it's going to go into 3. A lot of positive number times. All right. All right, so that's the answer to that one. This is out of order here, but when is this function less than 0? Well, I can see it, it's right there. Less than 0 from -5 to 5. But if you weren't sure, you could always do a sign chart. Those are the critical numbers that make zeros. And you could put a number in like 1,000,000. Well, 1,000,000 here makes a positive, parentheses, 1,000,000 there makes a positive, and 3 is positive. And I think you divide 3 plus signs, I think you're not. I don't think you're less than 0. I think you're bigger than 0. So I would say false. These y values aren't bigger than 0. These are, and these aren't. These are less than 0. These aren't. You take an x, you're getting a positive y value right there. Take an x, you're getting a negative y value right there. And we want to be less than 0. And f of x is another way of writing y. Y's are less than 0. All right, so I got to make some space here. It's taken more than 10 seconds to erase it. All right, we did that. We did that. We did that. Now we're graphing y equals 1 over the square root of x. I threw a little monkey wrench in here. All right, you really got to think about this. You got to really think about what the graph of y equals 1 looks like. I'll use a dotted line. The square root of x. And so I'm dividing the square root of x into y equals 1. Well, what do I see as I look at the square root of x? The y values are getting bigger very slowly, but they are getting bigger and bigger and bigger. So what happens when I start dividing 1 by a big, and then a bigger, and a bigger, bigger, goes in fewer times. Let's actually show some numbers. 2, it just got bigger. It just got bigger. It just got bigger. That's a pretty small number. I think I'm heading to 0 out here. I think I'm getting some asymptotic behavior, actually. I think I'm getting y equals 0. Now what happens over here? Well, look, right there's nice. That's the intersection of 2 graphs. There's a y value, that's 1, and the square root of 1 is 1, and 1 divided by 1 is 1. So my actual graph passes through that intersecting point. Looks like it's doing this. And I think I got to have an open circle there because I don't think I can divide by 0. But I think this little amount fits into 1 lots and lots of times because I can make that little amount equal 0.01. I think that fits into 1 an infinite number of times. But there's a domain restriction here. Can't divide by 0, and I can't use negative numbers. So now let's erase that. Let's erase that. Let's show an arrow there. That's what my graph would look like. That's what 1 over the square root of x is going to look like. All right, so I just wanted to do what, I wanted to call it a composite, but it wasn't really well, I don't want to misstate something. So that was what the graph looked like. All right, 4x plus 10. 4x plus 10 over 2x minus 9. What do I see? I see an x-intercept of minus 2.5, minus 5/2. That's when this fraction equals 0, when the numerator equals 0. Positive 9 over 2, 4.5. So we'll put that here. Positive 9 over 2 is undefined because it gives me division by 0. I can see that each of these is to the first power, so I'm going to get sign changes at each of these locations. I can see that 4x divided by 2x is equal to 2. So if I put really big numbers in here, we don't care about a 9 and a 10. It's really the interaction, and these are the same exponent. So when the exponents are the same, it's a division of the coefficients. We keep having these conversations. Hopefully it'll make some sense to you. I can see the y-intercept. Let's get rid of this. Let's get rid of that. Let's get rid of the parentheses. And if you plug a 0 in, I think you're dividing those constants. So near -1, minus 10/9. All right, I'll try to keep this as simple as possible. Sign changes. And that's what that graph's going to look like. Logarithm. Got another log here. All right, so it's the inverse of decay. So it's going to look like this. It's going to look like this. We did one a little while ago. So what makes the parentheses 0? 5. So there's my domain restriction. I need numbers bigger than 5. If we're talking about the inverse of growth or decay, time to amount, well, then these are the amounts back to time. And if you don't have some kind of amount that's decaying or growing, you don't have a growth or decay problem. So I got to have numbers bigger than 5. My first differential is going to be 1. My next one's going to be 3. So when you're doing logs like this, you want the parentheses to equal 0. That gives you your asymptote, your x equals asymptote. X equals 1 is going to get you 2020. And x equals 1/3 is going to get us 2024. So set it equal to 0, set it equal to 1, set it equal to the base. All right, so what makes this a 1, a jump of 1, which is going to be this first jump right there. That's going to happen when x is 6. So we should get, when x is 6, we should get 2020. Let's throw it through and see if that happens. 6 minus 5 is 1. What is log base 1/3 of 1? I hope you're saying 0 times 4 is still 0 plus 2020 is 2020. My next asymptote is going to be 3. Okay, so what makes x minus 5 equal 3? I do believe I want to put a 2 in. Nope, I'm sorry. I want to put an 8 in. Oh yeah, towards the end of the video. All right, 8 minus 5 is 3. And so that's going to get me -1. -1 times 4 is -4. That's going to get me 2016. Okay, let's actually show this. There's the 3. What exponent do you put on top of 1/3 to get 3? -1. Done. Exponential function, I can do it here now. All right, we got asymptotes of 30. Asymptotes, we've got differentials of 30 and 15. We've got an asymptote of 4. We want an x equaling -1, and we want an x equaling, we want to make this 1/2 to the 1, so we want 4. Those are my two x values, so this one is going to be 4. 15 and 4 should get me 19, and this one's going to be 34, and that should happen when x is -1, and we should get a graph that looks like that. And I'm talking to you, so it takes me more time. You want to be able to do that in your mind's eye. So let's actually see y equals 4. All right, so this thing is decaying. Half of 30 is 15. Half of that, 7.5. Let's just pretend it was 16. If you cut 16 in half, you got 8. If you cut 8 in half, you got 4. If you cut 4 in half, you got 2. If you cut 2 in half, you got 1. If you cut 1/2, you get in half, you got a 1/4. I think you can see this thing's going to 0, which means it's heading to 4 over here. That's our end behavior, y equals 4. Drop a -1 in. -1 makes 1/2 to the 0. 1/2 to the 0 is 1 times 30 is 30 plus 4 is 34. And let's drop a 4 in. 4 plus 1 is 5 divided by 5. It gets us 1/2 to the 1. 15 and 4, 19. Okay, so you got that one. Another cosine curve. Okay, we can do that. So we're going to go bumpity bumpity. All right, max to max. Centered at 7. Going up 5, 12, going down 5, 2. So there's our range, 12 to 2. Put in a 6. and then 1 revolution. Multiplier is 1, so the period is 1 into 2 pi. Always take the multiplier times x divided into 2 pi, and you have your period, which is a distance, and that distance is pi units to the right from 6. That will take me to 12. That will take me to 12. So therefore, 6 plus pi over 2 should take me to 2. Let's show that one. 6 plus pi over 2, 6 plus pi over 2. Let me make sure I said the right thing here. Pi or cosine of pi over 2 is 0, so that gets me 7. So I just made a mistake. I'm not quite sure where. It's correct. So at the end of the video, always happens to me. Brain gets tired, haven't had my coffee. 6 plus pi over 2, pi cosine of pi over 2 is 0. Okay, x minus 6 equals 2 pi. Oh, that's why. Yeah, this should have been 2 pi. Sorry about that. All right. I think I said the right thing and then just lost my train of thought. But when you got the period of the function, you want the period of the function to equal 0, which is the start of the revolution, circumference trip, and x minus 6 equals 2 pi. Right, so I don't know why I said pi's, but corrected it now. So 6 plus pi. If we do 6 plus pi and we subtract the 6's, then you're at pi. Where's pi on the unit circle over here? What's that width? -1. So that's going to be your minimum value right here at 6 plus pi. So a lot of symmetry. Started to lose it at the end there, but we got our practice in, and that's what's important. Now, any one of those functions that you haven't got down to 10 seconds or less, go to the playlist. There's rapid fire 5. You do five in a row. You'll move in the right direction. You do it for a couple of days in a row. Yeah, look at each of these graphs, 30 seconds each day, and 4 days later, you probably got them all. But you got to do them over a repetitive period of time. If all you do it is for 2 or 3 days and then you don't see it again for months, good luck remembering. But if you do it a couple of, 30 seconds every day until you get a handle on it, then maybe every week you see one. Then maybe every 2 months you see one, it's still going to be with you. And you're going to be able to take it through your future classes, which is absolutely necessary. Otherwise, you got to drop out of math, which is why everybody does. All right, you got my lecture, double lecture there at the end. Good luck practicing.